Hello, statistics students. Welcome back to Chapter 8. So we've covered Section 8.1a, which is hypotheses, right? So now we're building and we're going to keep working towards doing hypothesis testing using the traditional method. So first of all, when we're doing hypothesis testing, we're making a decision about our null and our alternative hypothesis. So our decisions are made based on sample data, right? That's the best we've got. We don't have all of the population information. So if the evidence against the null hypothesis is strong enough, we will reject H sub O. If the evidence is weak, we will not reject H sub O. So those are our options. We've got to decide, and that evidence is using our data that we've got, our sample data, using a confidence level, using critical values. Remember, whether we reject or not reject our null hypothesis, this doesn't prove that it's true or false. The only way to prove something absolutely is to use the entire population. So statistics, even a hypothesis test, does not prove anything absolutely. We need to know, the only way we can 100% know is to use the entire population, right? That's why we say we're 99% confident. The only way we can be 100% confident is to have every single piece of data that we could possibly have from our whole population. So we are going to talk about our significance level. So significance level goes along with our alphas, goes along with our confidence level. These are all intertwined. So this is, we're looking at how large of a difference between X bar and mu in order to reject or not reject our H sub O. So how large that difference is. This is, significance level is the probability of making a type 1 error. Remember we talked about type 1 and type 2 errors. Type 1 error is alpha, so the probability of a type 1 error is alpha. And remember, that's underneath our bell curve, right? We go to that Z table. This is all interconnected. Our most common significance levels, our alpha is at 0.10, 0.05, or 0.01. And if we were thinking about confidence levels, when we did our confidence intervals, that would be 90% confident, or 95, or 99. Those are our most significant levels. And just so that you know, we do have a probability of a type 2 error that is beta. It looks like a sort of a B, like this. We're worried about alpha now, so don't worry too much yet about our type 2 errors. Alpha is what we're looking at. That's our probability of our type 2 error. So in the box here, if we're talking about rejecting our H sub O, we always assume that H sub O is true, so we don't reject it unless there's significant evidence to reject it. And in the real world, our most common way to see that is a person is innocent until proven guilty. We always assume that a person is innocent until there's significant evidence to say that they are not innocent. Okay, so we always make the assumption that H sub O is true no matter what our claim is. So let's talk about what this looks like visually. So we've got critical and non-critical regions. Remember, alpha is our shaded area. It's the area underneath the curve. We're still looking at our symmetric or our normal or bell curve. So the critical region is also known as the rejection region, which I really think is really a nice way to see it. So over here shaded is the critical region. That is where we're going to reject H sub O. And I know this is long, but this is, sorry, I have to sneeze. excuse me. This is a range of test values that indicates there is a significant difference between x bar and mu, and h sub o should be rejected. Notice down here in this lower one, where we're shaded to the left or it's less than, my critical or rejection region is that small shaded area. Notice that right here, this is alpha equals 0.01. Non-critical region then is also known as the non-rejection region. This is where if anything lands in this non-rejection region over here, we do not reject h sub o. So for those of you who are visual people, that helps you out. We'll make a curve. We'll say, well, here's our alpha and here's our critical value. Does the critical value fall in the critical region, or does it fall in the non-shaded, non-critical region? So the non-critical region is the range of values that indicates the difference between x bar and mu was probably due to chance. H sub o should not be rejected. So here H sub o should be rejected. H sub o should not be rejected. So that's what it looks like. This is what we're going to be talking about. So let's talk about the critical value, right? I mentioned critical values in our critical region. So critical value, we call it the CV. Critical value is, whoops, it separates the critical region from the non-critical region. So this actual line right here is the critical value, and in this one we have two critical values. It's a separating line. That's all it is. It's here's where the difference, here's where the separation is. So you have to choose a significance level, alpha, which is the complement of the confidence level. So we know, say that our confidence level is 92%. So therefore, we know that our alpha is 8% or 0.08. They're complements, right? They add up to 1, they make a whole. So we have to talk about one and two-tailed tests so that we know what those look like. This is a two-tailed test because our critical region is in the left and the right. We've got two sets of shaded areas. We've seen this before when we used our z values. By the way, our critical value for a lot of this is going to be our z values, so don't throw away that z table. We will still do t's and we will still do chi-squares. So all those things carry over from the last chapter. So let's talk about how you can find critical values for specific alpha values. Table E is that table in the back of the book. Really important. You probably want to have it. So the first step, I'm going to tell you, you don't have to do this forever, but if you ever ask me a question, I'm going to say draw it. Let's draw a normal curve and indicate what we're talking about. So when we indicate the appropriate area, left-tailed means that the critical region is on the left side of the mean, or it's shaded to the left, right? Just like we've always been doing. Right-tailed is your critical regions on the right side of the mean, so we shaded to the right. And two-tailed means that we've got to divide our alpha by 2 because we're splitting that equally on the two tails because it's a normal symmetric curve. So we can have one-tailed or two-tailed. The one-tailed is either right or left. Step 2, when we go to actually find our critical values, we're going to use alpha. For our right-tailed, we're going to use 1 minus alpha because it's to the right, right? And we always know that a symmetric curve, our z critical values are shaded to the left, so we have to do 1 minus alpha. And for two tails, don't forget to do your alpha over 2. When we're saying that we're going to use alpha, we are going to go to our table. So in many of these particular cases, to start, we are going to do jump into the Z table to find the CV, the critical value. So when I say use alpha or use 1 minus alpha or use alpha over 2, we jump into the Z table, work our way out. Now, obviously, if we're using a chi-square table, we're going to do it a little bit differently, but we're still doing these the same. And I want to make sure you see why you don't do alpha over 2 for our one-tailed tests. So this is one-tailed and one-tailed. So if it's one-tailed, you need to know, is it right or left? And don't forget, if it's left-tailed, you're going to be shaded on the left, which means that you are going to have a negative critical value. If it's right-tailed, you're going to have a positive critical value. If it's two-tailed, because it's symmetric, you're going to have the same value. It will be positive and negative. So for a one-tailed test, notice I put this picture again. We've seen this already. This guy up here on the top is a right-tailed. This one on the bottom is left-tailed because it's shaded to the left, because this one's shaded to the right. I don't know if you can see it right here, but it actually tells us what the critical value is. So remember, in a one-tailed test, it doesn't matter if it's right or left. When we calculate the test value in the next section, if that test value is in our critical region, we are going to reject H sub O. Don't forget, if it's left-tailed, your sign on your CV will be negative. If it's right-tailed, your sign on your CV will be positive. It makes sense when we know that this is a standard normal distribution. 0 is in the middle. It's the center of the universe for our mu. Everything to the left is negative. Everything to the right is positive. If we are going to, let's do an example. So let's suppose the medical researcher chose to use a 99% confidence level, and the alternate hypothesis is that the mean pulse rate is greater than 82 beats per minute, mu is greater than 82. So first of all, I don't like that I didn't ask you to do H sub O and H sub 1, right? What's our null in our alternative hypothesis? The null is always equal. So it always has an equality. So for this one, we would say that mu is equal to 82. We would say that our alternative hypothesis is this. Mu is greater than 82. So then I would ask you something like, is this left-tailed or right-tailed? And you would probably tell me that it's right-tailed, right? Because it's shaded to the right. If I were to look at this, that means I'm saying, okay, mu is here at 82, and I'm saying in my alternative hypothesis, so my mu is in the middle at 82 equal to, I'm saying, well, I think that mu is greater than 82. So this is my rejection region or my critical area. So I'm going to go ahead and I'm going to say, all right, well, alpha, if I'm at a 99% confidence level, 1 minus 99%, alpha is equal to 0.01. So then we go into our Z table and I search for, however, you've got a couple options. Some people are going to start to see sneaky things. By the way, I should have written down right here that this is a right-tailed. So if I'm going to look this up in my Z table, when it's right, I said I need to do 1 minus because I know that this is 0.01, but remember everything in the Z table is shaded to the left. So you could look up a 0.9900, or you could look up the 0.01 and you could put a positive sign on that critical value. Some people are going to be sneaky about this. When you look up a 0.9900 on your Z table, you are going to end up finding a 2.33 for your critical value. If you looked up 0.0100, you would get negative 2.33. It's in between two values. Remember, go with the larger absolute value, critical value, and you'd end up with a 2.33. So talk to me if you're struggling with that. Let me know if you're having trouble. But if it's a right-tailed, it has to be a positive critical value. So suppose that same medical researcher chose an alternative hypothesis that the mean pulse rate is less than 82 beats per minute. So my H sub O is still mu is equal to 82. My H sub 1, they're saying now they want to change it. It's less than 82 beats per minute. So if I draw myself, mu is equal to 82, but now this researcher is testing the hypothesis that mu is less than 82. That's going to be to the left. So that means then I've got myself a left-tailed test, right? I'm looking to see, is that legitimate? So if I keep the same alpha, same confidence level, 99%, and that comes out to 0.01, right? Notice I didn't divide that by 2 on either one of these because it's only on one side. I have 1% left, and it's on the right in the first example, on the left, and it's not getting split up at all. So on this one, for my left-tailed, this is 0.01. So when I look up 0.0100, I know that it's shaded to the left on the z-table. So if I just look up 0.0100, I would end up with a negative 2.33. Hopefully that's not all that new to you. We did a lot of looking up things in, chapter 6, I believe that was. So there is our right and left-tailed. So a one-tailed test, you don't have to split alpha up. Let's talk about a two-tailed test. So when the research question is about whether the mean is different from a particular value, as in the case of an alternative hypothesis that the mean pulse rate is not equal to 82 beats per minute. So our H sub O is still mu equals 82. But now our H sub 1, it's just not equal to. It's not 82 beats per minute. So we just say mu is not equal to 82. So if it's not equal to it, we can use that. So we can say, okay, well, here is mu equal to 82, and I don't think it is. So I think that my average number of beats per minute is either lower than 82 or higher than 82. So I'm looking to see if it's on either side of that. I don't know how big that critical region is. We will talk about that as we go. So let's say that we're sticking with our same 99% like we did in the last one. So I could say my confidence level equals 99%, which means what's my alpha equal to? 0.01 still, right? 1 minus 99%. But I've got that 0.01 that's going in these two sections. We're splitting it equally on this symmetric curve. So that's got to be 0.005 on either side if I split it up. So alpha over 2, 0.005. So don't forget that for your CV. So now I'm going to go into my z-table. I'm going to search for 0050. And I'm going to look and see what that is. When I search for 0050, I'm actually looking for this CV right here. But I know it's going to be a perfect symmetric match to this CV down here. So I'm going to have one negative and one positive, same values. So when I look up 0.00500, I believe that gets me a positive and a negative 2.58. My CV is different if it's a one-tailed or a two-tailed test, even if I have the same confidence level. So make sure you watch out for that. You have to know. So remember, this is alpha over 2 because I'm splitting that up nice and evenly. All right, so let's see. What else do we have to talk about? Okay, so I'm going to ask you to figure out critical values. And this is a big thing. You should probably highlight this or put a big star next to this. This is also on page 425 in your book. This is going to be the last step, step 5. Oh, I've got it written right here. For every single hypothesis we do. So we've got 4 options, right? If we reject H sub O and the claim is H sub O, we're going to say there is enough evidence to reject the claim that the mean number of heartbeats is equal to 82. If our claim is our alternative hypothesis, but we reject H sub O, we're going to say, oh yeah, there's enough evidence to support the claim that the mean number of heartbeats is greater than 82. If we don't reject H sub O and our claim is H sub O, right, there is not enough evidence to reject that claim. And if we don't reject H sub O, but our claim is H sub 1, we'd say there is not enough evidence to support the claim that the mean number of heartbeats is less than 82. So notice every single one of these is different. So make sure you pay attention. As we go through these, we will come back to this page many, many times. So mark it, highlight it, put a sticky note on it, whatever you need to do. Last but not least, as we're going through this chapter, if our population parameter is mu, right, we all know that the first one is the population mean. So our test statistic is going to be X bar. That's what we can use in place if we don't know mean. And we know that our standardized test statistic, our critical value, maybe I should say that, our CV that we're going to go to is either Z, or in some cases we might need a T. Right? Depends on if we know sigma, all those kinds of things that we've talked about in the past. If our population parameter is P, remember that's proportion. That's the proportion of the population that has walked into something while texting. So our test statistic for that is P hat. Hopefully you remember that. And our critical value for P hat and P problems is always going to be our Z critical value. And last but not least, sigma squared, hopefully remember that that is population variance. So our test statistic for that one is going to be S squared, our sample standard deviation. We could say here also variance or standard deviation. These are both variances. And when we had variance, this was the weird one. This was the one that we had to go and we used our chi-square values. Chi-square. So those things are not going away. And I just wanted to make sure that I mentioned them here as we're starting to get into the chapter. We will use all these. We're going to start with mu, just like we did in the confidence interval chapter. So that is it for section 8.1b. Thanks for hanging in there. This was fun, and we'll get to testing next.